Hello, everyone. Welcome. I'd like to first introduce Professor Vishal Misra, who is the Senior Vice Dean for Computing and AI at Columbia University.
Good afternoon. Welcome all. Thanks, Asaf. Welcome to this event on sustainable cloud computing and AI. It's the first event we have for our week on climate. So this is a climate week at Columbia Engineering. There's a series of events. This is the first one, so welcome. Hopefully you can join us for more of these events. But for this event, I want to thank Asaf for putting it together with Sharon. I see Sharon somewhere here. Sharon Spitz of DSI and Alexis Abedisian. And also I want to thank IBM and DSI for putting it together, and of course all the panelists and speakers. So, the topic that we are here on, it's a very important topic. In fact, my own position has been created recently. So last year, Dean Shifu Chang asked me to, he first created this position for Vice Dean of Computing and AI, and then, I was honored that he asked me. And typically when you take these positions, people say, congratulations, and then you correct them. No, it's condolences, but so far so good. So, this is an important topic, right? My own area is, before I started dabbling in AI, is in data centers and networking. And, I've known Musharraf and Ramya for the longest time. We work in similar areas. So this is an area of great interest personally for me, but or for society as well. The ChatGPT moment has seen the use of AI explode. And, initial estimates when ChatGPT came out were that each ChatGPT query took about 100 times the energy of, let's say, a Google search query, which was by then the most important or the most popular thing that people used to do on the web. Then people started saying, oh no, it's not so good, there's hallucinations and all, so we don't have to worry about it, it'll die down. And then, things like Perplexity took over, it became so popular. Google is moving towards, having AI, and Bing, generative AI as part of every search. So this trend is not going to go away. But we have to be responsible, we have to be ethical about the use of energy. And I think events like this will help us come up with new ideas, new architectures where, AI is becoming an important part of our lives. But how do we do it sort of smartly, ethically, and sustainably? So with that, I welcome you all, and thanks, Asaf, again.
Great. So just before we start, if you're interested in getting more information about Columbia's efforts on electrifying the energy system, feel free to scan the QR code. I think there's a newsletter that's going to be available, kind of following the events of this week. Okay. Great. Okay. So my name is Asaf Sidon. I'm a faculty here at Columbia, and so. Thank you all for coming here. So just the audience contains a really great mix of Columbia affiliated people, students, faculty, and staff, but also we have a lot of guests, external guests. I saw in the registration list people working in large companies with sustainability roles or that are interested in sustainability. We have also folks from NGOs, from the investment community, from government. So welcome all. I hope today's event will be kind of useful for this kind of broad set of people. So of course, the rise or the demand for compute didn't just start with ChatGPT a couple of years ago. It's been going on for decades, right? With the proliferation of compute on our phones, in our pockets, on every appliance we use, and then of course in these data centers, which are football field-sized warehouses that have 100,000 servers or more, which obviously consume a tremendous amount of electricity and emit a lot of carbon. But I'd say that so far, up until a few years, right, we've been somewhat fortunate that this rise in compute and demand for compute has been met with also a significant kind of exponential improvement in efficiency. We've seen these efficiency gains across multiple layers, from better cooling of the data centers, better power delivery systems, of course, better, more power efficient, energy efficient hardware and circuits. And then even on the software side, we've seen developments like virtualization and containerization, where back in the day you'd have an application that consumed an entire physical server, but today you can pack multiple applications, multiple workloads, and on the same server, or even on a small number of cores. So far we've kind of been able to curb the energy consumption of compute. The rough estimates are it's about 1% to 2% of the world's electricity goes to data centers and cloud computing. But unfortunately, a lot of the efficiency gains that I mentioned have already been kind of maxed out, right? So just as an example, one of the metrics that people use for efficiency is what's called PUE, which measures basically the amount of power that if you put in a certain amount of power into a data center, how much of that power actually goes to power the compute versus other things like loss in transmission or cooling, for example. And so if you look at like state-of-the-art data centers from companies like Meta and Google, we're basically close to the optimal number there, almost 1. So there's really not much more kind of efficiency on the system and even the hardware side to squeeze away. But of course, our thirst for compute is only, we're getting thirstier and thirstier. And there are these projections that say, that in about 10 years, right, if today the electricity consumption of data centers is about 2%, in 10 years it might be tenfold. It might be 20% or more. And then, at some point, theoretically, maybe it will consume all of the world's electricity. I doubt it's going to get there, but this is a real kind of impending challenge that we're facing. And of course, the elephant in the room, to Vishal's point, is the rise of AI, right? Where there's a very clear relationship between the amount of compute you pump into training models and their accuracy and usefulness, right? So companies are racing to build these huge data centers, which will only be used to train even a single model, right? And so you can imagine how much energy and carbon these facilities are going to consume. So this is kind of a really big challenge that's facing our kind of community of computing infrastructure at large. And so today, hopefully, you'll get to hear some ideas on how different folks, both from industry and academia, are thinking about these challenges and possible solutions for them. So we'll start So we'll have 3 talks. The first one will be from Tamar Elam at IBM Research. He's going to tell us about the challenge of AI sustainability. Then Musharraf Chowdhury from University of Michigan, who's going to talk about energy optimal AI systems. Then Ben Lee from UPenn is going to talk about his work on sustainable AI in data centers. Then we'll have a panel on AI. We'll have a short break in the middle. And for the panel, we'll also be joined by Ramya Raghavendra from Meta Fair Infrastructure and by Udit Gupta from Cornell Tech. So have kind of a really, hopefully, interesting set of speakers and panelists today. So with that, I'll introduce Tamar first. So Dr. Tamar Elam is an IBM Fellow and Chief Scientist for Sustainable Computing at IBM Research. Tamar is leading research aimed at drastically reducing the carbon footprint associated with computing across infrastructure systems, software, and AI. She got her PhD from the Technion and has been at IBM, I think, for 24 years. And she was and she's recognized as an IBM Fellow in 2014. And she's really a leading figure in kind of promoting the challenge and solutions to sustainable computing and AI. So thank you, Tamar. Just one more thing. So the talks, at the end of, we'll have room for questions at the end of the talks with people with mics that will take questions. So thanks.
Okay. Yeah, where do I find my presentation? I'm not sure. Oh, here we go. All right, there are more people that are coming, so please come in. There are more seats. All right, so let me tell you just a little bit about myself. How did I get to work on sustainable AI or sustainable computing? My background is actually in cloud computing, distributed computing. My PhD was on actually theoretical computing science, algorithms, and so on. But in 2019, I sort of became obsessed with climate. I actually went to a conference, ICSI, and Steve Easterbrook of Toronto University gave a keynote there about climate, and I just couldn't stop thinking about it. So I went back to IBM and I started asking everyone, what are we doing about this problem? And long story short, oh, that's not Asaf. That's not. You put the wrong. You put it in the last chart. you're like, yeah.
Sorry.
Oh, okay. Here we go. I don't know how to use this. It's not a Mac.
I know, me too.
Okay. Yeah. So I started working 100% on sustainability, and my conviction is that in order to address climate change, we have no choice. We must use technology and science. We need innovation in order to address climate change. So that's why I'm working on it. So I call my presentation the AI energy problem, resonating with the very, very famous Horowitz presentation, the computer energy problem. But I do think we have a problem there. Now, this is not working. Tell me it's working, but it's not. Maybe this is working. No. Okay. So let's talk about the problem. I call it the two-head. And by the way, so before I even start, this presentation, a lot of contributors from IBM Research and from universities that we're collaborating with, including Columbia University, MIT, UIUC, and many more universities. And so there are too many people that I can put on one chart. That's what I wanted to say. The other thing that I wanted to say is that I worked on it during the weekend because I did give presentations this year in ASPLOS and in E-Energy and other places, but this area changes so quickly that whatever I did is already no longer relevant, so I needed to come up with a new presentation. So I came up with this little monster that says the two-headed monster. Why is it two-headed? The first problem is that the AI models are getting bigger and bigger. That's the issue. We have a problem with AI scalability. The problem is that in order to get to this new, everyone wants to get to the new capabilities, like groundbreaking capabilities, we need much bigger models. And if we need much bigger models, the computational resources correlate with that exponentially, okay? It's monolithic by design, or maybe it's monolithic by design today, and the easiest way for companies that have too much money, let's put it this way, to get to the compete over the new capabilities is just to pour money and energy and building these monsters, really. So look at these charts, like the charts are speaking for themselves. This is the growth of AI models, the number and how many flops, floating point operations per second, are needed to train these models. And that obviously correlates with energy and with cost. And you can see here, like GPT-4, like how big it is and how much energy it requires. It says here 51773, 1,000 megawatt hour could power an average US home for 100 years. So you can imagine how much energy these models are they need. Okay, so now let's go to what's the second head of the monster. The second head of the monster is that we reach the end of Dennard scaling, also known as Moore's law. So what does it mean? It means that, and Asaf alluded to that as well, we used to every 2 years be able to run the same computation with half the amount of energy. And we did that by miniaturization. I don't know how to say it, but basically putting more transistors in a square millimeter, doubling the amount of transistors in a square millimeter. Okay, that's how we did it. But the problem is that we reached the power wall. So what's going on right now is that we reached the physical limits, and now we're starting to have problems with current leakage. Because of that, we're losing efficiency. So we just can't, and you see here, number of transistors grows, but the energy doesn't grow in the same correspondence to it. So we can't for free get more and more energy for the same. So basically improve our energy efficiency. So we can't keep up. We can't keep up with the energy demand. That's what's going on, and that's why it's a two-headed monster. And we're seeing it reflected in the data center consumption. So look at this. This is like, whoa, that's where I started. And whoa, we see this like growth in data center demand. And it's lots of different trends. It's not just AI. And as Asaf alluded to it, it's also that we already did all the easy stuff. Like the PUE, we already did the automation. We already did all the easy stuff we did. We have no tricks, no easy tricks in the bag anymore. And we have AI on top of that. So, all right. So what are we going to do about it? That's the question. So we need innovation to the rescue. We really, really do need innovation, and it's actually really fascinating. And I see two different areas, system innovation and AI innovation. Let's focus first on system innovation. So what we're seeing is, so think about it. With the general purpose chips, we can't achieve more energy efficiency. Using the usual way that we used for years that worked for us of miniaturization. So we need special chips. What is special chips? It's just chips that can't run every computation, that can run some computations, and they're designed to be more efficient for this type of computations. So we have a proliferation of accelerators, and all the big technology companies out there develop their own accelerators. Okay? And what is common across all these accelerators? They have central focus. They are focused on optimizing for matrix multiplication. Why? Because matrix multiplication is in the heart of AI. And if you think about matrix multiplication, and you can see it here, you have rows and you have columns. And what do? You multiply and add, right? So it's very regular. It's a very regular structure. Now, where is the energy going? So that's another thing. Where is the energy going? Where is it spent? It's spent between the processor and the memory. That's where all the energy is spent, and that's called the von Neumann bottleneck. Okay, so if you want to eliminate that von Neumann bottleneck, if you take into account the regularity of matrix multiplication, you basically want to reuse the data that is already loaded into the cache. That's the trick there. So everyone, and there is special structure for that. It's called systolic arrays, and everything is centered around that. Okay? And so here you see the hitting the memory wall, the von Neumann bottleneck, where we achieve more and more performance with the processor, but the memory is not keeping up, and that's why we have the bottleneck. Okay? The issue is, okay, we're used to improving the energy efficiency, like doubling it every 2 years, and that's not going anymore. I mean, there is a limit of how much we can optimize for matrix multiplication. At some point, it becomes harder and harder. Okay, we do what we can, right? But we need to keep improving. So the question is, can we come up with new innovation, with new innovative architectures? Can we break the von Neumann bottleneck? This is some of the open questions in this area of systems innovation. So before I move forward, I want to talk a little bit about the innovation that we do in IBM Research in collaboration with many universities. So like all the other companies, we also have our own chip that was built specifically for AI. It's called AIU Spire, and you see a picture of it here. It's based on the idea of a proxy, so a lot of ideas went there. It's a very innovative architecture with the bandwidth between the processor and the memory and so on. It's also based on the principle which is called approximate computing, where you represent numbers with a fewer bits. Lots of research work went into it, and now it's being integrated into our mainframe, which is a big achievement for us in IBM Research, because we like our technology to be useful. So that's the AIU Spire. But we go further than that. So remember, I mentioned the von Neumann bottleneck, North Pole, and there are multiple papers here that I cited, and I hope you're going to get these charts. In any case, I'm putting everything on LinkedIn, so just download it from LinkedIn. But there are Nature and Science articles about that. And what they did there is they said, let's come up with a completely new brain-inspired architecture where instead of ever having a processor and a memory like that, we have them merged. We have a network of nodes that have memory and processing capabilities and memories together. It's still digital, but it's still silicon, but this is how they do it, and they're managing to get much more efficiency, but the amount of memory is limited. So you can't run GPT 3 or 4 with that, but you can use it for visual recognition, things like that. And then last, we go to the more future stuff, and that's completely getting rid of silicon and going to analog. That's really about putting the computation in the memory. So here is another way to overcome that bottleneck. So looking at technology that does the computation in non-volatile memory and codes the weights in the non-volatile memory, and basically leverage properties of conductivity of the material itself to perform the calculation of, again, just matrix multiplication. That's it. That's the only thing it can do, right? It can multiply and accumulate. That's it. But it can do it way faster and way more efficient. So that's analog AI, which is much more experimental at this point. Okay, so let's now go to AI innovation. So what do we have here? So I already mentioned the modularity problem. This is, in my opinion, the biggest problem. It's the modularity. It's the fact that in order to get better, we need to have much larger models, and they're monolith. So all of you guys that know programming models and understand coding, you know you have procedures you call. We have modularity when you write code, right? We understand code structure. There is modularity there. It's there for a reason. But we don't have it in models. It's this neural network that we don't quite understand that well, okay? And it's not easy to take a neural network and break it to multiple parts and have each part much more efficient and have them run together. We don't know how to do it, okay? So, and that's where, and as I said, computation is exponential based on the size of the network. That's the question. Can we use smaller models to achieve the same results? Or a combination of thereof to achieve equivalent power of expression? That's where you have techniques such as LoRa, which is these adapters. So let's say I have a big model, I want to fine-tune it. I don't want to create another version of that huge, gigantic model that is fine-tuned for a particular task. I want to freeze the parameters. I want to create a little adapter. That's a type of modularity, okay? So LoRa adapters, tons of research papers on LoRa adapters out there. That's one way to address this problem. A mixture of experts is another idea where you're sort of breaking it to domain-specific things that are good in a particular domain, like coding or language, and you have them cooperate with routing and stuff like that. So that's another thing that people are investigating. And then on a completely different or parallel track, so if we talked about the architecture innovation, there is also platform innovation, which is the runtime innovation. And that's how we train these models. So things such as parallelism, data parallelism, pipeline, tensor parallelism, sharding, speculative decoding, and all of that goes into that area. But the biggest question in my head, like if you want to be really visionary and you want to look at that space and ask, what do we need, okay? How can we do that? Look at system innovation and AI innovation and do the hardware and software co-design. Can we come up with completely innovative architectures that are not transformer-based, like everyone are doing transformers, right? Maybe are more sparse. Maybe they just turn on and off just when you use them, like spiking neural networks that can work better, consume much less energy, and can we build the hardware for that to optimize it even much better? And so the hardware today is totally focused on matrix multiplication. The architecture is like there are 2 or 3 different architectures, transformer-based. It's like that's what. But can we just break out of that cave and look at the bigger picture? And can we really be innovative there? Anyway, what is IBM Research doing about that? Because that's where I work. So we have our own Granite models, and we use a lot of these techniques in the Granite models. For example, scaling, upscaling from a smaller model to a larger model. Granite comes with 13 billion, 20 billion, and 34 billion, okay? But in order to build, so every version, because it's bigger, it's better in accuracy and things like that, right? But do I need to start from scratch, or can I take the smaller model and build from it a bigger model and save a lot of energy this way? So we use technology which is called depth upscaling, where some of the lasers are frozen and some of them are copied, and this is how we do it. We have our own, like we're experimenting with mixtures of experts. So Self MOE is a collaboration between IBM and multiple different universities. When you break that model to multiple different experts in coding and that's, you do it without labeled code, and so again, and you save a lot of energy on also how you do it, but you get pretty good results there. Then when you go to runtime innovation, we're basically applying everything and combining all the optimization techniques. So things such as sharding and HSDP, FSDP-based pre-training, selective activation, checkpointing. It's how you do the parallelism, right? It's all about parallelism, so how you do the checkpointing. We're combining all of these techniques. And what we're finding is it's very hard to combine these techniques because they don't work together, actually. They conflict. Then you find bugs. And then you have to go and fix the bugs. It's a lot of work that we all contribute. We contribute everything to open community, basically. But it's a lot of work. And here is all of the PyTorch blogs that we wrote here. Describe all of what we did here. But after you get these optimization techniques to work together, you actually save much more energy, 30%. Like if you have 30% throughput improvement, you're processing more tokens, and you are already working on a high utilization all the time, then that translates to 30% energy saving. So that's the runtime innovation. And finally, platform innovation, or how you deploy the models, makes a difference. So we have our own watsonx platform, and we're building optimization into it, such as how you do the routing, the queuing, how you place on a heterogeneous, we believe in openness and heterogeneity, so heterogeneous infrastructure that may have multiple different accelerators. Because GPU may be good for training, but we may use something else for inference, right? Maybe AIU. So heterogeneity, and then how you do the placement, how you do the sizing, how you do the GPU slicing, how you do the caching to accelerate the loading time, and so on. These are all techniques that we're building into our platform. And I want to finish with on a good note, okay? So far I described how the problem is huge, but what I want to say is, look, AI is a powerful tool, and it can really help us fight climate change. And the other half of what we're doing in IBM is actually use AI to fight climate change. So things such as adaptation. IBM released a foundation model together with NASA to analyze satellite images in order to be able to predict in much smaller granularity events such as flooding and fires and so on, to predict climatic events so that we're more prepared. And it's open sourced. By the way, all the links are here, so you can go and you can actually play with these models. You can download them, you can play with them, you can interact with them. There is a really nice UI. So this is a geospatial analysis. The other thing that we do is around mitigation. So I'm a big believer that we can use AI to accelerate the scientific discovery because we can use AI to generate hypotheses. AI is actually a very creative thing. Like surprisingly, it's like it's good in creativity, in generating hypotheses, connecting the dots in ways that we don't see because we're biased, and AI is just biased in a different way, right? So sustainable material, for example, finding material to replace PFAS, which is a very toxic material which is used actually in manufacturing these chips and also in other products. Climate and sustainability, finding material for carbon sequestration and things like that. And life science, like accelerating the discovery of vaccines and so on. Again, there are some links here which you can read more. So that's my end statement, which is, okay, I guess because AI is so powerful, we can do so many things with that and even fight climate change. It's a very worthy goal for us to work together, and it's also fascinating, in my opinion, to find ways to make AI greener or more sustainable.
Hi, thank you for that. Jevons paradox says that the more efficiently we use a resource, the more that resource is used in total. Certainly the history of computing is that millionfold efficiency improvements have led to much more increase in total usage. So aren't we just working to get to that 20% even faster by, because you can just say instead of lowering energy use, you're lowering cost per operation. So you're going to make it cheaper to do things with AI. So how do you address Jevons paradox with this?
Yeah. I'm very aware of the Jevons paradox, and I actually don't have a good answer for this. I think that, we as scientists, what we can do is make things, or engineers, or we can make things more efficient, right? So we're not going to need as much. If society goes and use more, maybe there is room for policy and things of that nature.
Thank you very much. One question related to the previous question. Is there a measurable index to understand the throughput of AI systems and the energy usage per amount of capability? Of course, generative AI is one thing. If you do planning or reasoning, it's totally different. Even OpenAI with the new O has a different footprint of energy usage. But is any industry or scientific norm today to evaluate or understand the energy budget or footprint of performance, of AI performance?
Yeah, that's a very good question, and I think there are several attempts in that area. There is the Green Software Foundation. IBM is actually part of the Green Software Foundation, as well as other companies. I think Meta is there also, and Google. And we actually started a committee just on, so they came up with something which is called the Software Carbon Intensity, SCI, but they're now specializing it for AI, so they're not there yet. But we could look at things that what is the energy per token. When you do LLM, you generate tokens. So what's the energy per token, and try to reduce it. It doesn't give you the full answer, because maybe you can just use less tokens to solve the problem, right? So it's actually a harder question than you think to get to the right standard. What I want to do is I want to have a way to say this is red AI versus green AI when I'm giving or give it A, B, C, D, E, right? But that standard doesn't exist yet.
Hi, thank you very much for an excellent presentation. I have a question. You talked a lot about energy usage. What about the water usage to cool all of these data centers down?
Oh, wow, yeah. There is cooling. There is not only cooling, and I just didn't have the scope in that presentation to talk about that. Okay, we use a huge amount of energy to cool them. And I can tell you what we do in IBM, for example, in the Poughkeepsie data center, what we do when we do the water. The problem is you use water, but then they heat up, and then you need to cool them somehow. So you use a tower or whatever. We're using natural ways to cool them through by leveraging natural resources that are in the vicinity. So there are all sorts of innovative ways to address it. It's not only about cooling, it's also about the water consumption. Water consumption is horrific, okay? And it's also about toxic material that you're using in manufacturing these chips. And all of this needs to be taken into account.
Speaker. All right. So I'd like to introduce our next speaker, Musharraf Chowdhury. He's an associate professor of computer science and engineering at University of Michigan, Ann Arbor. His research improves application performance and system efficiency of AI and big data workloads with a recent focus on optimizing their energy consumption via the ML Energy Initiative, which he'll tell us about. He's done not only a lot of kind of award publishing academic research, but he's also had very high impact open source projects, including InfiniSwap, the first scalable memory disaggregation solution, Salus, the first software-only GPU sharing system for deep learning, FedScale, a scalable federated learning and analytics platform, and Zeus, the first energy optimal AI stack. And in the past, he was also invented CoFlows, and he was one of the original creators of Apache Spark, which I'm sure many of you are familiar with. So thanks.
Thank you, Asaf, for the kind intro, and thank you for inviting me. So I don't have to go through all of these slides, but because I took the time to put them together, I'm just still going to keep them up there for a couple of seconds so people can read through. I'm sure, unless you're living under a rock, it's it's been very difficult for the last few years to avoid this type of headlines that you keep seeing, that AI is going to, I don't know, take over the entire world, and the way things have been projected that we'll not have any energy left anywhere to the AI, and people are worried. And the reason they're worried is because we just don't have enough energy. Our growth is gated by energy, not by money, not by hardware, not by land. We just don't have enough energy to be able to build data centers up and running really quickly. And as a result, we are seeing this type of sub-headline under the headlines is that the plans for when certain coal mines should be, I don't know, stopped, will be decommissioned, are being pushed back. And you have seen probably in the last 3-4 days, Oracle, Microsoft, Amazon, everyone is trying to use nuclear power because we just don't have energy to keep going. And this headline is from maybe, I don't know, 10, 12 days ago. There was this meeting in White House, or I guess somewhere nearby, the AI folks and the energy folks and the DOE folks, they were discussing how can we get more energy delivered. And we care about all of this. One is sustainability. We don't want to make sure, or we do want to make sure that we can grow sustainably. But we also want to make sure that these advances in AI are equitable, because there are places where we don't have enough power supply and energy, and they may fall behind because other places they may have enough energy and AI will be deployed there, and they'll have lower latency access to AI. And in general, it's a concern of national security and future economic growth. And given that they are at a very, very high level, from 10,000 feet, we can go in two directions. We can increase and, I don't know, produce more energy, or we can try to, I don't know, figure out whether we can reduce the demand for energy. And I'm going to talk about some of our recent efforts into decreasing energy sort of consumption of AI, and in general, sort of our quest toward finding energy optimal AI. What is the minimum amount of energy we need given a model and a particular set of hardware? So together with many of my colleagues, we lead this project which we call ML Energy Initiative. It's ML Energy because before everyone started calling everything AI, people used to call it ML, and we've been doing it for long enough where we decided that we are going to call it ML Energy, and I didn't want to do a rebrand. But essentially, we want to understand precisely how much energy is spent and where, and then we want to optimize and reduce sort of the energy consumption. There was a question earlier, like how can we know exactly how much energy is going? That's what we want to do, and we want to then go further and optimize. And eventually, we want to expose what are the trade-offs between performance and energy and accuracy of model, and enable all of us and the developers of all these different software tool chain to be able to sort of make good decisions, what to give up to get what else. And so first thing I want to talk about, where do the joules go? We have all these joules that are being consumed and terawatts hour and such, and this pie chart is from a recent paper by some of our collaborators and Microsoft. I am not involved, but essentially they are looking up sort of how much power is being provisioned, and about 50% of the power provisioning of an AI server, a typical AI server, goes into sort of for the GPUs. They are the biggest power draw, or that's what people assume. And many of these headlines that I showed earlier, they are based on how much power have been allocated, then they are multiplied by however many GPUs are in a data center. Then they get an estimate of this is the maximum power consumption. So for last few years in my lab, we've been building this software platform called Zeus, which tries to precisely measure actually how much power, energy is being consumed by whatever AI you are running. And the reason I have this code example is because that's all it is. To measure how much energy it takes, you create that one thing, and then you say begin and end window. Then you can get the energy consumption. Of course, it's thousands and thousands of line of code in the back end, but the front end interface is as simple as that. It's how you measure time when you write a computer program, begin and end, and you subtract. we wanted to build an interface where not just us experts and such, but all our undergrads, everyone using computer can easily measure and understand, so that when they see it's this many joules, they can get a sense whether it's too long or too short. Like we can see, okay, it's 5 seconds is too short versus maybe 5 minutes is longer than that. So people can understand. So I'm not going to talk about the tool itself, how it works, but I'm going to talk about some recent results that we got by using that tool. So these are many of the popular open source models. These numbers are collected maybe 2 weeks ago. My student took the time to run all of them. These are running on A100 GPUs by NVIDIA. And you don't have to go through all of them. It's just too much data. What I want to talk about that there are different types of generative AI models. We tried LLMs and code generation, multimodal models, and image generation, video generation. The y-axis is what is their average power consumption and divided by the maximum power draw possible by the GPU. And as you can see, for LLMs that are in black, they cannot, even if they want to, they cannot draw at the full sort of power availability that have been allocated for them, simply because they are memory bound. Their compute is much lower. I mean, they are basically underutilized. For image generation, video generation, they have massive sort of computation going on, so the orange bars are much higher. So when we see these numbers about this multiplied by that, they're often wrong because the actual numbers are not one, especially when we are talking about LLM. And these numbers are also varying based on hardware decisions. It's the same set of models. Instead of running A100, if you use H100, as you can see, all these average over max, they became smaller because these things are drawing more but running quicker, and energy is integration over time of power. So you end up actually consuming less energy. So things are getting more and more efficient. We cannot just take some number and multiply and project in what is going to happen in 2030 and go above like 100%, because a lot of efficiency is happening in the hardware level. There are efficiency also happening in the algorithmic level. These are just 2 bars I picked, and there are many, many insights that I don't want to go into because of time. And you don't even have to understand the details of what these different types of attention mean. But you can see that the 2 models I'm pointing to are from the same family from Microsoft, Phi 3. One is smaller, the other one is actually double the size. But the one that is double the size is consuming less energy than the smaller model, because it is using attention, which is sort of the core computation of an LLM, that is much more compute sort of efficient. So the total compute decreases, and you can actually significantly improve the energy consumption. So by actually doing algorithmic work that the previous speaker also pointed out, you can improve. By doing hardware improvements, we can save energy. And there is a lot of opportunities in the software level that we can save energy with. So I will get back to the software part, but first I want to plug this ML Energy leaderboard that we also maintain. So you can go to the URL where we, every 3 to 6 months, we update with the latest Gen AI models and precisely how much energy they consume on the GPU. So it's only the GPU part. The other part we are still working on and expanding our software tool chain. And then the other interesting feature, it may go down because we don't have that many GPUs, but you can give your live query and you can, I don't know, ask, and then the service will actually run your query and take some random models and generate output, then tell you exactly how many joules it consumed in live, basically in real time. You can go right now. It should be up. So the other question I want to talk about is, well, we know, okay, there's a lot of measurements and we figure out there's a lot of energy. How can we optimize energy consumption? And just in software, the model remains the same, no touching accuracy. The hardware remains the same, no changing hardware. And we have all these estimates, and there were some numbers that were shown earlier as well. And I just wanted to point out that 1 megawatt hour is basically burning 1,140 pounds of coal. And so when you have all of these megawatt hours, you can multiply by that and get a sense of how many gazillion pounds of coal you have to burn to produce that much energy. So we are going to now reduce energy from all of them. And this part is going to be a little bit technical, so I apologize, but I will try to make it as simple as possible. I couldn't figure out a simpler way of explaining it. But models are getting larger. The models don't fit in a GPU. So models are divided across multiple GPU, which are these 4 GPUs it's been divided into. Each of the boxes are computation. F means forward, B means backward. We don't have to understand too much of it, but they are computation that have to be run. White space means nothing is happening in that GPU. X-axis is time, time is going by. And we are computing across all of these different GPUs at the same time when we were trying to train this very large model because it couldn't fit in a single GPU. The part we care about is this blue line. This is the sequence of computation that dictate how long the entire computation will take. These computations depend on each other. When one is not finished, the next one cannot be started. And end to end, the critical path decides how much sort of time you will end up spending. This particular time is 3.83 seconds. It's real number when we ran GPT-3 1.3 billion model on sort of across 4 GPUs in 4 pipeline stages and 6 micro batches. So these are drawn to scale. This is what we find using Zeus. Say if we just take PyTorch and you just, I don't know, run it, and then things are being run, or you use Megatron LM or DeepSpeed or whatever framework. The color code they are showing, these are A100 GPUs, it goes from 0 to 300 watt, and sort of how much sort of power is being drawn. And across different computation, you see in the background is blue because nothing is happening. It's probably just blocking or very low power state. And all the other computation, they are running at full speed and drawing as much as possible, finishing compute. So what we found is that by carefully controlling all the other computation outside the blue line, we can slow them down to the point where they are the slowest, but they are not slower than the critical path. So as a result, we can save energy from all the computation outside the critical path. So the work that my student is going to present in a couple months is basically an algorithm that decides both across GPUs in space and over time, all of these tiny computation that are happening in millisecond granularity, how to set frequency in a synchronous fashion precisely to save all of this energy. And this is something that we call energy bloat. There is a lot of energy that goes sort of basically for nothing. We are just wasting them, throwing them out, and we could save all of this energy by not changing hardware, not changing algorithm, just simply in software precisely controlling how much power we should sort of give to which computation in what GPU over time. And again, the entire thing and is just this. Again, like the on is again a lot of stuff in the back end. But what you have to call is the same Zeus monitor, and then you have to pick an optimizer. This is a pipeline training happening. So we have a pipeline frequency optimizer. And then it is integrated with Hugging Face transformer library, so you don't really have to do very complicated stuff. You just add a callback to the optimizer. And then the optimizer will automatically, completely in software, figure everything out for you. And so what I want to sort of finish with is Zeus is a open source project developed in the University of Michigan, and we've been working on it for many, many years now, and we want all of you to try it out and collaborate and extend it. It's being led by my PhD student, J1, with the help of a bunch of other PhD students, undergraduate and master student, and there is a lot of other contributors that are outside Michigan. I don't know all of their name because you just know the GitHub ID of when they're contributing. Zeus have been downloaded, I think, from the Docker image we have like close to 150,000 times. We don't know who downloaded it, but the counter increased, so hopefully someone downloaded it. We know that we didn't download that many times. And the ML Energy sort of is a growing consortium of faculty across University of Washington, MIT, CMU, and also Columbia. Your own Asaf Sidon, he is one of the founding members of this ML Energy Initiative. And with that, I would like to stop there, and I'd be happy to take questions.
Okay. Hi, this is Tang, a current master's student at Columbia. Just trying to go into this research field. I think I like your talk. It's very exciting. So my question is, so you mentioned the Zeus versus the ML Energy Leaderboard, right? This is two projects that you're working on. One on like energy consumption of machine learning, like learning model training, one on like serving. So I want to ask a question: if like, which one do you think have more potential of like optimization in terms of the energy consumption, or what's the proportion of the like the two aspect of the AI versus sustainability research?
So that's a very good question. So some published numbers from big companies suggest that there is a 30-70, 40-60 split between cycle spend in training is the smaller one, and inference is often the bigger one, because you train once, then you are now fine-tune many times, serve millions of users. You don't have to train every time serving, so you probably end up spending a lot of energy in serving. Both of them are significant. It's not 10-90, it's a pretty substantial amount. Research-wise, training is somewhat easier to tackle because it's repeating iteration after iteration. It's same thing happening over and over again. Inference is much more challenging, so we are slowly getting into optimizing inference energy consumption. We were just, the leaderboard just sort of maintains how much they take, but inference is somewhat unpredictable. You don't know what request will come, how many tokens or whatever image will be generated. And so it is, from a research point of view, difficult, but at the same time more interesting, perhaps. But training also has a lot of interesting pieces. As you have seen before we did this Perseus work, when my student came up with it, I also was not sure we'll get this much sort of room to extract out of them, this much bloating happening. But I mean, we did find it. And I think in general, any topic, if you go deeper, there is always more interesting things to find.
Yep. Thank you.
Yeah, thank you very much. That was very interesting. I just wanted to ask how much scalable Zeus is. Is it to talk about one GPU optimization, or could that be supported to expand into the whole data center?
That's a very good question. So Zeus has multiple optimizers. So one of the original paper of Zeus that I didn't talk about was for small models and their end-to-end run. The last part, the second half, when I said, okay, optimizing the energy bloat, that is for very large models. So this one, for illustration purposes, was only 1.3 billion parameter. But in our experiments, we have experimented, or at least simulated, when it gets really large, up to 175 billion parameter, which of course we cannot run because we don't have that many GPUs. We have run up to few billions of parameters directly, and then we profiled and we put those numbers into a model to calculate what will likely happen at sort of even larger scale. The software itself, there may be some scalability challenges when you go to very large scale. One of the good part there is that even when you are training on 100,000 GPUs, say, it is just small sort of templates that are being repeated many, many times. So you have a model, and that's divided equals maybe, I don't know, 32, 64 GPUs, whatever. That is being repeated thousands and thousands of times, because at that scale you do data parallelism. And your model parallel or pipeline parallel, they don't have to scale at that level, because then you will lose efficiency. So when Perseus or Zeus are working, they don't necessarily have to worry about going to 100,000 scale, because it's just the same thing replicated side by side many times. So it should scale well, but we haven't really run it because we don't have that many GPUs to run it.
Yeah, understood. Thank you very much.
If anybody wants to donate GPUs from Sharp,
Yeah, I need to create a URL, ml.energy donate.
Hi, thank you for that amazing talk. I just wanted to know, when you talk about your energy thing. And when you talk about slowing it down, the critical path remains the same.
Yeah.
But you're saying that other optimizations can be slowed down, right? Is that what?
Other computations can be slowed down because they don't have to finish before, they just have to finish before the slowest one.
Yeah. So how does this exactly translate into less energy consumed? Can you explain the
So
back end?
essentially, what we have here, and I don't want to take over too much time, as you can see that each of the computation, the ones that became, instead of like peach color, they became whiter, they became wider, so they run at a lower power draw, but for longer period of time, and integration of power over time, that number becomes smaller. It may not always be the case. So in the paper, we try out many different models. Some of them we get very good improvement, some of them not so much. It depends on the sort of imbalance of the model. That's where some of the algorithm sort of work may come, how the model has been architected, and how much imbalance it has, and a variety of other factors that are involved.
Okay. Thank you. Thank you so much.
Thank you. So how does the energy growth come into being? What's happening outside this critical path? Are they performing useless computations, or are the cores running at an unnecessarily high frequency, or?
No, they are useful computation, but they are running unnecessarily fast. And if you slow them down a little bit, you can save energy without actually slowing down the overall computation. It's sort of like when you have to, give an assignment and you have time until midnight, finishing before midnight actually doesn't give you extra grade. You just have to finish within midnight is the same idea. And then you have to submit on time so you don't get penalized. And that's what we are trying to do, but in a different domain. The challenge, the technical part is, how do you do across multiple GPUs and over time and figure out the precise frequency and set them? Great. Thank you.
Right. So our next speaker is Professor Benjamin Lee. He's a professor of electrical and systems engineering and computer information science at UPenn. He's also a visiting researcher at Google in the Global Infrastructure Group. His research focuses on computer architecture, energy efficiency, environmental sustainability, and security. His research on environmentally sustainable computing in collaboration with Harvard recently received an Expedition Computing Award from the NSF. He received his postdoc in EE from Stanford University, his PhD in CS from Harvard, and his BS in electrical engineering and computer science from Berkeley. He's also an IEEE fellow and an ACM distinguished scientist. Thank you.
Right, good afternoon. Wonderful to be here. Thanks so much for the introduction. Really great comments from the earlier speakers. Really excited to be here to have this conversation. This talk will be to discuss maybe 2 or 3 years of work we've done in this space, giving you a sense of the lessons learned and maybe some of the future directions moving forward. So as many of you have seen from earlier talks, we're concerned about the massive growth in AI computation. The size of the models is growing exponentially, right? Increasing data volumes, increasing training costs. Beyond the training, I think, increasingly we're concerned about inference. What happens when you've trained the model and you've deployed it? How many prompts, how many queries are going to be issuing to these models, and how much energy and how much power will those prompts and those queries consume? Historically, we've been shocked by very large training numbers. I think the inference numbers are increasingly uncertain because we don't know what the final use cases will look like. We don't know what the application deployments will look like. But these are the numbers we're concerned about. This growth in AI demand has led to growth in data center capacity. I like this particular figure from McKinsey, which shows the rate at which data center capacity is growing. So we have time on the x-axis, and we have power consumption on the y-axis. This is data center capacity measured in gigawatts. And we have 3 different types of data centers we think about. The first is hyperscalers, the ones that are run by Google and Microsoft and Amazon and so on. We have colos, so these are massive facilities that are built so that people can put their machines and and put their workloads into these shared facilities. And then finally, we have privately operated data centers shown in the gray. For example, Columbia might run a data center here on campus that would fit into this last category. Across the board, we're seeing rapid growth, annual growth rates of 10, 15% in data center capacity. And I should note that these numbers were compiled by McKinsey before the advent of generative AI. So many of these numbers might actually be larger than the ones we're seeing here. As folks have noticed in earlier talks, this is a particularly challenging time to see such massive growth in AI and such massive growth in data center capacity. And that's because the traditional drivers of energy efficiency and sustainability are beginning to lose steam. The first trend that we are seeing run its course is a shift to cloud computing. Over the last two decades, we've seen fewer and fewer people computing locally in their own data centers and moving into Amazon's cloud computers, Microsoft cloud computers. And those systems, as other speakers have noted, are run incredibly efficiently. There's no way that a private data center operator could get the same level of efficiency as some of these hyperscaler data centers. And that's why a study from Science showed that even though we computed 6.5 times more between 2010 and 2018, total data center electricity use only went up by 6%. That's a huge growth in computational capacity for relatively modest increases in power. But as you can see from this figure, most of the computation that has been already moved to hyperscalers or to colos has already happened. Relatively little compute is being done in on-premise enterprise computing. So there's not too much left to shift that gray into those super efficient hyperscaler data centers. The second trend that was alluded to earlier from Tamar was this plateau in semiconductor scaling. We know that Moore's law has slowed, which means that it's been harder and harder to make those transistors smaller and smaller. And moreover, even as those transistors get smaller, they're not really becoming that much more energy efficient. And that translates into fundamental challenges when it comes to designing more power efficient processors. Trends that gave us increasingly efficient CPUs may not carry us towards more efficient GPUs as we move forward. I should also note that compute will also not be getting that much cheaper over time. Now that sub-figure in the upper left corner is particularly interesting because it shows how many transistors can you buy per dollar. And as you can see, in 2010, 2012, 2015, we're seeing a plateau, which means that the traditional economic efficiencies driven by Moore's law are no longer playing out. Yes, we can build larger chips with more transistors on them, but they're not going to be that much cheaper than the previous generation of chips. And then finally, the third reason we're concerned about data center capacity is local grid stress. It might be fine if we were to take all of this data center capacity and distribute it uniformly across the United States. But in practice, we find that data centers are clustered in particular geographic locations, like Northern Virginia. And there's been a lot of discussion recently, a lot of news about how 20% of this local grid energy might be going to feed a large cluster of data centers. And as a result, Dominion, the local utility provider in that region, will be unable to meet its sustainability goals on time, on target, because of this massive growth in data center capacity. We see similar data coming out of other places like Ireland, where local data centers are putting undue stress on very specific parts of the grid. So what is causing these challenges, and what might we do to try to address some of these challenges? This is actually work that we've done in collaboration with Meta, starting in 2021, where we were looking at AI and its carbon effect. And when we think about AI and carbon, there are really two sources or two contributors to the carbon footprint for AI computing. This first graph is actually from Udit Gupta, who's here in the audience. He found in 2021 the cost of manufacturing hardware. So embodied carbon is really the carbon footprint of semiconductor manufacturing, electronics, and building out those computer systems. And in this particular study, if you're looking at consumer electronics like the iPhone, most of the cost carbon footprint of that computing is in the manufacturing, the integrated circuits, electronics, and others. The cell phone doesn't really draw that much power, so we're not really worried too much about the energy usage. We're really talking about manufacturing all of that electronics. And of course, we have the other side of it, which is operational carbon. Operational carbon relates to the energy being used. And for operational carbon, we care, this is a huge issue in data center computing, right? So when we look at the operators of the largest data centers in the United States, collectively they consume more power, more energy than the state of Massachusetts. And okay, so maybe that's a little bit better. Okay, so collectively, these data center operators are consuming more energy than the state of Massachusetts and may approach the energy usage of New England as a whole. This data was compiled by David Brooks at Harvard. Okay, so we have two contributors to the carbon footprint: embodied carbon, manufacturing the hardware, and operational carbon, running all of that hardware. Now, when we look at AI, Carol and others at Meta looked at recommendation models, and they looked at a language model. This is a transformer-based language model, and they studied the share of the carbon footprint associated with manufacturing the hardware and then running the hardware. So we can see that the operational carbon is fairly large, and the embodied carbon down at the bottom is also fairly significant, but not as large. And this is true for a variety of recommendation models, but also a language model. Now, many of these data center operators, like Google and Meta, will say that they are net zero. And what net zero really means is that they are investing in renewable energy, like wind and solar, and they will accumulate these credits for running those investments. And at the end of the year, they'll look at how much energy was produced by those investments and compare them against data center energy usage. And if those investments cover data center energy usage, then we can say that we're net zero, and otherwise we might have some work to do. Net zero has a variety of caveats that we'll talk about later, but this is what most of these hyperscalers mean when they're talking about net zero. But embodied carbon is fairly significant. Now, there are a variety of ways we might be able to improve energy efficiency. And indeed, there are teams that are focused on improving that efficiency over many years. We can imagine improving the hardware through better specialized design. We can imagine improving the hardware through domain-specific acceleration and improving performance per watt. We can imagine improving infrastructure. Infrastructure means maybe optimizing how we schedule and how we run the data center. And then finally, we could rethink the model architectures. What kind of machine learning do we want to do? And all of those things can contribute to energy efficiency. So in this particular study, Carol and others have found that every 6 months, you might be able to reduce power by 20%, a factor of 0.8. And now if you compound this over a period of 2 years, you might say, well, I got a 20% reduction every month for 4 periods, every 6 months for 4 periods. Does that mean I'll have a 60% reduction in power at the end of that period? Do we get this compounding of efficiencies? And unfortunately, the answer is no. And this is because of the earlier question we saw about Jevons paradox. There is a question about how much more compute we will do as that compute becomes more energy efficient. Even though in this particular study we reduced power by 20% every 6 months, total system power fell by only 30% over 2 years. And the issue is, how do we quantify the rebound effect? How do we quantify how much more compute we did even as that compute became more energy efficient? And this is not actually trivial to answer. Even economists who have studied this a long time for lighting and for electric vehicles and so on, there's very little consensus. It's very difficult to quantify this effect, and it's much harder for computing. But I think we need to think a little bit more deeply about that question and try to quantify how much more compute we do as compute becomes more efficient. So moving forward, we're thinking about the solution space for data center design and sustainability. And this, again, is another project that we published in 2023, again in collaboration with Meta and Bilge Ekun. And here we're looking at the way we power data centers and looking beyond net zero operations. So today, data centers will invest in wind and solar energy, and they will connect to the grid, and they will also sign power purchase agreements with the utility providers so that whatever energy is produced by those wind farms or those solar panels will count towards credits that the data center can then use to offset its operations. The key point here is that this accounting or this offset is calculated at the end of the year. So there will be many days within that year where the sun doesn't shine or the wind isn't blowing, but the data center will still compute. Yet, by the end of the year, as long as those credits match your data center energy usage, then you can claim net zero. So that's what it means to rely on offsets for these sustainability goals. The problem with relying on renewable energy alone is that there simply isn't enough renewable energy. When we look at data coming out of the US Energy Information Administration, we see that historically, the amount of new renewable energy capacity on the grid is about 7% per year, growing at about 7% per year. But the difficulty is that hyperscaler data center operators, their capacity is growing at 25% per year. So we have this large gap that's becoming ever larger because of these very large differences in the compound annual growth rate. So this is a fairly significant concern. We also see this for co-location facilities, and if you care about manufacturing semiconductors, we also see this for the fabs, for the chip fabs. Right? So we can't rely on renewable energy alone to get us to sustainable computing. The other reason why we can't rely on renewable energy alone is, of course, this well-known intermittency or diurnal activity pattern that we see in the generating sources. This is particularly evident in California because California has a lot of wind and a lot of solar energy. But what they're finding is that they can't find enough consumers to take all of that energy off of the grid when it is most abundant. So in the middle of the day, when you have a lot of solar energy, there simply aren't enough consumers of that energy, so they have to curtail it. They have to turn it off. So they're deactivating solar energy, separating it from the grid because there aren't enough consumers during particular times of day. And what the challenge they're observing is that across time, you're seeing more and more of this renewable energy being curtailed because there's this increasing mismatch between the supply of renewable energy and then the demand for that energy. So this leads us to a natural solution, which is demand response. Can we modulate the demand for power in response to signals that we're getting from the grid? So again, data centers could invest and receive credits from renewable energy generation, but maybe instead of matching on an annual basis, they match on an hourly basis. So in hours of the day where there's a lot more renewable energy, can we compute more? And when there's much less renewable energy, can you compute less? This will require fundamentally rethinking how we build data centers so that they can store energy when renewable energy is abundant, and then maybe perhaps reschedule or defer computation to periods where renewable energy is more abundant. So we did this pathfinding study where we said, what happens if you wanted to rely solely on renewable energy to get to carbon-free compute, 100% of your compute being done with carbon-free energy? It turns out that this gets prohibitively expensive very quickly because of diminishing returns. Suppose that you got 95% coverage. That means 95% of your compute is done with renewable energy. To get that last 5% coverage, you're going to have to deploy 5 times more renewable energy than it took to get from 0 to 95. Right? So we're seeing this in a couple of different geographic locations. The X and Y axis shows solar capacity and wind capacity, and the Y axis shows the coverage of compute. And we see in Oregon, it'd be great to have a mix of solar and wind. In North Carolina, they're relying on solar alone, and no matter how much solar you deploy, you can't get 100% coverage. You max out at 54. And then here, Utah is able to get a fairly large percentage coverage through some combination of solar and wind. So we need to think more in a more balanced way about renewable energy installations. We might think about deploying utility-scale batteries, and we charge up these batteries when the renewable energy is abundant, And we can then estimate how large these batteries have to be. So this shows on the two axes how much solar capacity you've got, how much wind capacity you've got, and then how large of a battery do you need to get carbon-free compute. This is measured in hours of computation for the entire data center. So these numbers are fairly large, so if you rely solely on batteries, those batteries will get big very quickly. You might want to compute 8 hours of a day using battery power, for example, or 10 hours in a day using batteries. Utah, the numbers look a little bit more reasonable. Utah says that given the wind and solar mix, if you can compute on batteries for 3 hours in the day, 4 hours in the day, that might get you to carbon-free compute. I'll say here that these numbers are big, and if you assume $350 per kilowatt hour for energy storage, we find that these costs of building these batteries might be on the order of $100 million. That's big, but that's still a small percentage of the total cost of building out the data center. And then finally, what happens if you want to flex up and compute more when there's more solar energy? It turns out that you're going to need extra compute capacity, extra servers, extra flexibility, so that during the middle of the day when you have lots of solar energy, you can flex up and do a lot more compute. How much more compute? This figure shows maybe 20 to 30% in Utah. In the middle of the day, you're going to need to be able to do 30% more computation when that renewable energy is abundant. Right? So this might require deploying additional servers that sit idle for a large part of the day, but then turn on when renewable energy is abundant. So all three of these solutions give you a sense of what the possibilities are, and the key here is to find the right mix of these three solutions that minimize operational carbon and also incur modest embodied carbon costs. So how much wind and solar do you deploy? How much utility scale battery capacity do you deploy? How many additional servers do you need? Figuring that out will have some implication for your operational carbon and also some implication for your embodied carbon, because you're building out additional servers or you're building out these additional batteries. And trying to find the right balance is going to be increasingly important. I'll close by saying that we're just getting started in this space. We are launching a new expedition in computing. This is a large National Science Foundation funded project. NSF has invested $36 million in 3 projects for energy efficient and sustainable computing. Of this, Penn and Harvard are leading a team with a $12 million project on improving the sustainability of compute. This is the team of 14 professors across a variety of schools. A third of the team is at Penn, a third of the team is at Harvard, and we have a variety of other faculty contributing from other universities. I'll just note that we are engaging with folks in the business and policy community. Arthur Van Bentham is at the Wharton School, and he's giving us a sense of what scenarios we might encounter when it comes to energy economics and the grid. I'll also note that we're working with Adam Weirman at Caltech, who's thinking about reinforcement learning for robust decision making when you think about who gets to compute when. Yuan Yao is an industrial ecologist at Yale, thinking about LCAs and how we reason about the embodied manufacturing costs of carbon. And then because he's sitting right here, I'll mention Udit Gupta at Cornell Tech, who's been leading a lot of our thinking on embodied carbon in manufacturing. Okay. So the objectives of this proposal or project are threefold. First, we need better data. How do we do carbon accounting, measure and attribute the embodied and operational carbon of computing? Once we have a sense of the numbers, how do we mitigate this footprint? We're seeking to reduce total carbon footprint by 45% over the next decade relative to a 2020 baseline. And then finally, we want to have impact, which is to say we are engaging with industry partners, we're engaging with lawmakers and the regulatory environment to shape their understanding of the problem and also the solution space that we care about. I'll mention that we need carbon modeling and energy economics. They will feed the decisions and the strategies we take to mitigate embodied carbon and also to mitigate operational carbon. And then we're going to be targeting key applications in artificial intelligence and virtual spaces so that we can see how much of an impact we're having on the broader system. I'll close by saying this is an academic project. We are engaging with a variety of community participants from academia and PhD students and so on. We are engaging with industry. We have partnerships with Google and Meta and others. And we are also hosting workshops at the National Academy of Engineering, trying to shape the discussion and influence how policymakers think about this problem. And then finally, we are engaging with the broader community and encouraging people to think about many of these questions. So in summary, I think we've got a really great sense of the problem. I'd also say that we have a really great sense of the solution space. It's just a question of which combination of these solutions we'll take. I think the future of AI, I'm a computer scientist first and foremost, so I'm really excited about the future of AI. I don't want AI to be constrained by sustainability, by energy, and I think many of these issues, if we get them right, many of the solutions, if we get them right, will enable further capabilities in AI, even as we deal with the challenges that we've outlined today. So that's it. Thank you very much. Happy to take questions.
Hello. Thanks for the presentation. Two questions. Considering the increase of consumption of data center companies and hyperscale as well, what is, in your opinion, the best solution for the curtailment in the renewable source? Another question is related with the local grid, Express, and what's your opinion about the decided when a hyperscale needs to decide to invest in US or in another country to develop a new data center?
Sorry, can you repeat the first question again? I didn't get that first.
How can you manage the curtailment problem?
Yeah, so the curtailment problem is interesting. I think we need to have flexible hardware systems that can flex up. Like there was a lot of discussion about flexing down, which is to say when you feel like your program doesn't need that power, you use less power. But we should also be able to flex up, which is to say, if there is energy available, can we consume it and get useful work done, right? So the shifting across time is going to be incredibly important. Allocating compute across space is also going to be incredibly important. I think that really goes to the question about the availability of renewable energy and how much infrastructure already exists. I think there's a lot of concern, rightly, about data centers coming into a community requiring a lot of new energy infrastructure and then passing on those costs to ratepayers in the community, right? People are paying higher electricity bills because there's a data center coming in and there's a lot of new energy infrastructure being built. So to the extent that if infrastructure already exists, then that could be a good way to influence data center site selection.
Hi, thanks for your talk. One clarification, thanks for bringing up Jevons paradox, but in it you mentioned system. So when you said it was like, instead of being 60% less, it was only 30% less for a system, but Jevons, of course, means there will be many, many more systems. So which was it? Was that a single system you were talking about?
That's a single system. That was a data center, a cluster within a particular company. The macroeconomic effects are super hard to reason about, and we've reviewed some of the literature from econometrics and others, and even there are huge error bars for relatively mature technologies like lighting or electric vehicles. So the macroeconomic effects are harder to reason about.
But it may be over 100%, even in that particular case.
That is true.
But getting back to the main part of what you were speaking about, using renewable energy for AI, we saw a previous headline that said coal plant shutdowns are being delayed because of AI use. And that AI use might be 100% renewable. It doesn't have to be coal. It's just that the renewables could have replaced coal in other applications. So can't we consider that even though we're running on 100% renewable at an AI center, it's really running 100% coal?
Yeah, exactly. So I think you're right. So if you read sustainability reports from all of these companies, they will very much focus on this term, which is additionality. Additionality says you are investing in renewable energy, and that renewable energy would not have been deployed otherwise. There is a question about whether or not that is true, given that only 7% I think there could be a lot more installation of renewable energy if there were more money, or if there were more infrastructure for transmission lines and so on. So I think the question about additionality is a hard question. And I also think there's a regulatory question involved. Right now, data center operators are self-policing or self-governing in some sense. They set their goals and then they define how they want to reach those goals. And I think the issue around coal is a good one, because if data centers are locking down very large amounts of renewable energy, then that's potential another industry that is not reducing their carbon footprint. So that there is a sort of regulatory aspect to that, I think, that we haven't explored.
One last
Thank you very much again. Great talk. Can you explain a little bit more when you mentioned that 5% improvement requires 50% more renewable energy usage? On one of your earlier slides.
This one here?
Yes.
Yeah, so suppose that it took 50 gigawatts of new renewable energy to go from 0 to 95. To go from 95 to 100, you have those 50 gigawatts, and then you have to add another 250 gigawatts to cover that last 5% because of the issue associated with the available, because you have to essentially deploy enough renewables for those worst 2 or 3 weeks of the year where you don't really have a lot of wind, a lot of solar. Yeah, you're still going to be you still want to compute. So covering those tail cases is prohibitively expensive. So that's why we think that batteries and rescheduling has to have a role to play. No one single solution is going to be cost effective, either from an economic perspective or from a performance perspective for the applications we care about.
Thank you, Ben. Okay, so I just wanted to introduce the two new folks who joined our panel. So Ramya Raghavendra is a research director at FAIR, Fundamental AI Research team at Meta. At Meta, her roles spanned across AI, compute, and data, both in production infrastructure as well as research. Prior to Meta, she was a research scientist at IBM Research. She's co-authored over 25 papers in top venues and was granted over 40 patents and earned the title of Master Inventor at IBM. In her previous life, she was also, unfortunately, an academic, did her PhD at UC Santa Barbara. And then Udit Gupta is an assistant professor at Cornell Tech, and he's been doing, also been working on sustainable computing now for several years, as you've already heard mentioned in Ben's talk. And he's been doing cutting edge research on sustainable computing and AI, and his research has also been adopted not only in the ivory tower, but his research has also been adopted at scale at companies like Meta. And he's won numerous awards, including Micro Top Picks, and his PhD dissertation received the SIGARC and SIGMicro Outstanding Dissertation Award Honorable Mention. So thank you both for also joining us. Okay, so I'll start by posing a question to all of you, kind of open question. Even now in the break, I've had a bunch of folks came up and said they're really, really kind of interested in pursuing research in this area. So in your view, what's kind of both in industry and in academia, what's kind of the biggest kind of open challenge in enabling sustainable AI? So Ramya, I'm going to start with you.
Thanks for having me here. Thank you. Wonderful to be here. So, to answer the question, AI is a transformative technology, and in its current growth phase, we are at a place where it comes at a significant cost to our shared environment. One of the biggest challenges with AI is that the amount of demand it places on the resources and the pace at which the demand is growing. So I think in terms of research challenges, if you break it down, fundamentally, we need to be able to answer how do we bend the demand curve. This exponential growth that we are seeing cannot be sustained for too long. How do you bend the demand curve? You heard about PUE approaching close to one. That you're as efficient as systems can be. So how do we actually make sure that the demand is something that the infrastructure and environment can meet? And we need to be able to make clean energy sources available to data centers when and where they are needed. And I think we need to be able to essentially understand the manufacturing process and learn about how we can bring them down. So I think these are three broad research areas where there is still a lot of work to be done.
Udit, you want to take a crack?
Hello, is this working? Cool. Hi, my name is Udit. So I guess to answer Asaf's question, coming from an engineering background, I like to be quantitative about as much of what I'm doing research on as possible. One of the big challenges, in my opinion, around sustainable computing is how do we even quantify some of these emissions? Like whether you look at a Bloomberg article, a Guardian article, a Financial Times article, there are always giant uncertainty bars or ranges that they put out of like AI could be emitting anywhere from N number of metric tons to like 3 times that or something like that. And so I think one of the big fundamental questions is like, how do we actually quantify this? So a lot of our research has started to look at this kind of life cycle perspective, going all the way from manufacturing and fabricating the chips to all the energy use. And whether you kind of sit across the entire computing stack on circuits and devices, to architecture and systems, to designing the models, to even more user-centric research, there's a lot that you can do in terms of raising awareness. And once you've raised awareness of how to actually quantify those emissions, what do you do with that data going forward?
So I think, like simply put, the biggest challenge is how to reduce energy consumption. I think we should focus on reducing demand and take a minimalist approach to figure out, from an algorithmic perspective, it could be what is the energy scaling law, like how much energy do we need to reach a particular target accuracy. Like people who are more, I guess, on the theory side, they could think about this. On the software side, I think we need to figure out what I call energy debugging, which basically goes to this point, like precisely being able to quantify and measure exactly how much energy went where, so we can eventually take actionable items. And I think from the hardware side, we need good metrics and counters. Like all the numbers I was presenting, they depend on NVIDIA exposing some counters, and we are hoping that they are quite accurate. We don't necessarily know sort of exactly how accurate they are. There are some research that exists. They say, okay, it's within 5-10% or so, but there are new hardware coming out all the time. And after saying those algorithmic and software and hardware, 3 different things, the biggest thing I would say is taking a cross-layer approach. We cannot be in each our silos and optimize these and that. We need to consider all 3 aspects and whatever else comes in the entire life cycle of all the entities that are involved, and try to optimize, co-optimize them, as opposed to doing individual optimizations.
I guess I'd have 2 different comments. One is for the students in the room studying computer science and electrical engineering. I think it's going to be incredibly important to be able to reason about computer systems and computer architecture in ways that maybe we haven't had to think about as much over the last 5 years or 10 years, when it's really about programming and developing new algorithms and developing new AI techniques and data science. I think all of those things continue to be incredibly important. But I think as some of these earlier talks were mentioning, it's not possible to think about power efficiency or carbon costs of manufacturing unless you know something about how microprocessors work or how memory systems work and so on. So for the students in the room studying some of these technical areas, really getting some breadth and going a little bit further down towards the hardware, I think would be incredibly helpful. I think for the people who are not in computer science or electrical engineering and maybe coming from like industrial ecology or environmental science or some of these other areas, I would just say something that came up early in the talk is there are these fantastic numbers that are showing up, right? And then the reality, when you actually measure things, look quite a bit different. And I think we're seeing a lot of that in the media as well, that these exponential claims, we're going to run out of energy. I think If we take the analysis 1 or 2 steps further and look at things on the ground, I think refining those numbers is going to be incredibly important, and going 1 or 2 levels deeper in the analysis will be incredibly important.
Great. So now just some follow-up questions. So you mentioned that one of the biggest challenges is kind of even just quantifying the carbon consumptions across the entire life cycle. And I know you've done a lot of research in this area. So where do you still see open gaps in our understanding of carbon emissions in data centers?
Yeah, great question. So I kind of think about this at different layers of the computing stack of how do we make carbon accounting more accessible to everybody, whether you're a researcher, whether you're a consumer of a technology. So kind of starting at the bottom of the computing stack, if you're thinking about devices and circuit technology, right? If you have a new device technology, whether it's emerging non-volatile memories, chiplet technology, 3D integration, being able to answer the question of, well, we can start to, and there's a lot of emerging research of how do those technologies impact performance and power efficiency or energy efficiency, but the carbon impact of that we really don't understand, right? So that's a great area of research, especially if you're a PhD student, or if you're in industry as well. I think that's a great area to look into. Going up on the stack, right, on the systems perspective. If we start to think about an entire AI server, we start to think about training, there's been some really great work from Microsoft that at the data center scale, one of the things that they're seeing is a lot of the embodied carbon is really stemming from storage and memory devices. And a lot of the power consumption in our data centers is really coming from CPU, GPUs, the compute portion. And so kind of reimagining how do we design and account for these trade-offs between memory and storage versus compute, I think is really fundamental in how we design systems, and having better accounting for what is the cost of data, right? Like just having a data set lying around in your data center is extremely costly from a carbon perspective. And then going even above that, right? Like I mentioned, there's user-centric research. We had this really cool survey that we did recently where we posed a question to people of, if we told you that your ChatGPT queries were actually consuming 10 times fewer carbon, would you be okay with sacrificing a little bit of the quality of that experience, whether it's slowing down your processing times and things? One of the surprising things we found was people said, yeah, actually, if you tell us that you're going to save sustainability or carbon, we might be open to those sort of trade-offs, right? But that brings up a lot of fundamental research questions of, well, how do I tell an individual person how much carbon are they responsible for? Cloud providers are really interested in this because cloud customers want to know, well, I used N number of servers for this amount of time. Please tell me my associated carbon impact, right? So these are really, these are some of the questions I think could be great to answer going forward.
Ramya, I had a question for you. So from your vantage point at Meta Fair, so obviously, all of us are playing around with, all the latest language models, and some of us have incorporated them in our day-to-day lives even. I'm sure a lot of students are using them for their studies. But looking a bit ahead, we know that they're not the end-all, right? We're starting to get used to language models, but we're going to have new models coming up in the future, other type, video generation, multimodal models. How do we think about these new generations of model as it relates to sustainability?
Yeah, that's a great question. I'm just thinking about what it means as we look forward to multimodal models. What Udit just said resonates a lot. The data sizes are getting bigger, significantly larger. So I've been tracking data set sizes that goes into pre-training for the last 4 years. I've been doing this at Meta, and we went from a few gigabytes to now petabytes size data sets that goes into training these models. So storage, you need to power storage devices. Having a data set sitting around is expensive. Processing those data sets and figuring out, you're doing data ablations, you're doing annealing, there's a number of things you need to figure out what is the data mix that goes into these models. And all that takes a significant toll on how much compute we dedicate towards the data pre-processing steps. These models tend to be larger. We are still very much within the scale of, very much within the realm of scaling our data set sizes and the parameter sizes, which means that, you can see these hyperscalers talking about procuring hundreds of thousands of GPUs in the next few years. So you can think about how this is going to increase the demand on power, energy in the data centers. So you have to now think about reducing the operational emissions coming out of these, the demand on operational cost, and as well as the embodied cost that comes with building and powering up these large data centers that are required for multimodal models. Pre-processing the multimodal data sets as well as the training takes much longer when you're talking about video data sets. As a result, there's a lot of research into how do we develop multimodal accelerators for AI, which means, and the more you go into specialized ASICs, you're winning on the operational efficiency side of things, but you're contributing more and more to the embodied cost of these things. So if you look at how embodied and operational have shifted in Meta, when I first started looking at this, we were talking about 40% of our total emission carbon was coming from embodied versus the 60 from operational, and that's flipped in the last 3 years where we say 70% is embodied. So when you sort of make progress on one, it is important to also see how it's affecting the other. So I think these are the things to keep in mind.
Feels like you solve one problem, you create another problem with sustainability. That leads me to my next question. So, I think we can somewhat wrap our head around operational carbon, which is kind of the carbon that consumes by actually powering, the electricity, basically. But it's a lot harder, at least for me, to wrap my head around embedded carbon, right? Which is the carbon that is emitted, let's say, manufacturing a CPU or a GPU or a DRAM DIMM. So how do we even go about, as computer scientists, electrical engineers, to reduce the embedded carbon footprint of data centers and AI? Do you have any thoughts?
Well, I think on the embedded side, it's really a question about how we procure hardware and how long we run it for. So the classic 3 Rs: reduce, reuse, and recycle. In the data center context, it will be incredibly important. I think in terms of reusing hardware, I think the question is to what extent we can do differentiated refresh of hardware components within a data center servers. Right now, servers are commissioned and decommissioned as a monolithic entity, I think. And the question is, well, maybe processors like CPUs are progressing at some particular rate, GPUs are progressing at another particular rate, DRAMs and emerging memory technologies progress at a third rate, and maybe they wear and at different rates. Maybe they have different reliability characteristics, different aging characteristics. So can we build servers and can we architect systems that we can do modular replacement or modular refresh so that we're not replacing all the hardware every 5 years or whatever it is. And I think that may require changing how we think about connecting and organizing the various components in the system.
Any other thoughts? Nope. Okay. I think Ben mentioned this a bit earlier, but again, so for the students, again, so a lot of students are very idealistic about in general, right? And a lot of people want to work on sustainability. Any thoughts on the skills, like if you were advising someone who's kind of early in their career, I mean, you care about sustainability, and of course you're an engineer, let's say a CS or E major. What are the classes folks should take, or what what skills should they acquire? Do you have any thoughts? And this is a pretty emerging field, right? I don't think sustainable compute didn't really exist as a research area and academic domain even I think 5 years ago. So, any thoughts? Yeah, go ahead.
Yeah. So yeah, I love this question. I actually taught I designed and taught a new sustainable computing class last year at Cornell Tech, and we had students from ECE, CS, information science. We had students from the agricultural and sciences department as well. And one of the things that I think I learned from that was it's really helpful to take foundational classes and have a breadth of foundational classes as well, because sustainability really relates to a really wide variety of topics. In some sense, it's so exciting because as a computer scientist and engineer, you can take a paper that was written 20 years ago, 30 years ago, on like seminal ideas of like computational sprinting, on energy proportional server designs, on dynamic voltage and frequency scaling. And you can ask the question of, if I revisited this exact same topic from the lens of sustainability, would I write the same paper or would I change it? Or what about this changes, right? And so I think with that in mind, having kind of like a core computing background is helpful, but then taking a class maybe on power systems, taking a class in lifecycle analyses, go to your industrial ecology departments, go to your human-centered design departments, go to information science, take a class from there and see how do different people tackle different system design problems. I think that's really exciting.
Great. So this is a question for Ben. So you kind of mentioned carbon credits, and I sensed a little bit of criticism. I don't know if that's true, or at least that was my feeling. So what's your view on carbon credits? Are they even? So I mean, it seems like these companies are, using them. They can say that they're carbon neutral, but actually maybe their data centers are running on fossil fuels or even on coal, right? So is this a useful tool? What's the place of it? What are your thoughts?
I think in the near term, when there needs to be more investment in energy infrastructure, if technology companies are willing to invest and contribute, I think that's a good thing. I think that's perfectly a reasonable solution. So, for example, more renewable energy installations, more utility scale batteries on the grids, so that the grids can better manage the intermittency of all of this wind and solar, right? So I think there are fairly significant contributions underlying the generation of those offsets, and I think in the near term, I think that's what's needed. I think in the medium term or in the long term, say by 2050, when there is a lot more solar on the grid and there's a lot more wind on the grid, consumers will have to do demand response. Someone is going to have to do demand response, because as we see in California, a lot of renewable energy is going unconsumed, and that leads to inefficiencies, because maybe you might have to build more wind and solar than you might otherwise, because no one is willing to modulate their use based on time of day availability. So I think the bottom line is that I think in the near term it's fine. I think investments are good and infrastructure is needed. But at some point, someone's going to have to make hard decisions about how they consume energy and when.
Great, and this is a question from Rashaf. So you mentioned, like in your talk, right, that you providing this kind of very simple API that would give you the ability, like a developer, the ability to know, how much at least GPU energy was consumed by their model. So this is actually a new, right? I think this is kind of a pretty new approach, right? I think historically, if you look at like the engineering domains that thought about power, usually wouldn't be software engineers, right? Usually it'd be maybe hardware engineers or civil engineers, right? So what do you think is the role of software in solving this problem, and how aware should developers be of carbon and energy that's consumed by their applications?
Thank you. That's a very good question, and I think it's a very timely problem. Like, the way I see it, I teach so many students, and they know like how much time has elapsed, but they cannot, and I cannot also tell how much energy was consumed and how much carbon created. The reason I think we should build these tool chains is to make sure that they understand and they can debug and compare alternative solutions, and they can pick, because many of the decisions that are made at a very high level, developers that are far, far away from the hardware and the infrastructure, and when they sort of eventually propagate downwards, they're like, you may not have enough room anymore to optimize further because decisions have been made earlier. And by providing this type of tools, especially creating these cross-layer interfaces where users can provide some hint or express how much slack and leeway they have, those information could be used across many layers without everyone becoming experts of every layer. So I think it is going to be, very important to be able to build this tool chain and enable sort of everybody to understand what is the impact of even the simplest decision they make. And they can pick and choose and debug and figure out like what other things they could have done. And I think that will significantly affect sort of the overall impact of both energy and carbon at a much bigger scale throughout the ecosystem.
Great. So one last question for me, and then I'll open it up to audience questions. So what if we take, today we talked a lot about the challenges, obviously, and at least, I think some of the graphs and numbers you all showed are actually a bit scary, right? I think with the growth of compute and the fact that we've kind of maxed out a lot of the efficiencies, et cetera. But maybe we could take a contrarian view for a second, right? I know that Ben showed earlier the slide that like the annual growth rate of solar installations, at least historically, has been lower than data center growth. But if we take maybe more optimistic lens, it does seem that specifically solar is actually on kind of a quote unquote, it's not called a Moore's law trend, but it's basically a Moore's law-like efficiency trend where the cost is still going down kind of exponentially. And then the same seems to be true for battery, right? Density, where we're seeing very rapid gains. So maybe, this problem will be solved to some degree by engineers, but it will be solved not by us, but by battery engineers and solar engineers, and we'll have plentiful solar energy and batteries, and we won't need to care about all this, and we can just build as many data centers as we want. So, what do you think about this this point of view?
I can take a shot at it first. So, in the short term, we are not there, anywhere close to that. So around 2019, 2020, when big companies, Meta, Google, Microsoft came forth and said we are going to take these ambitious net zero goals for 2030, where we are going to be, net zero, some in case of Meta across our value chain. So if you look at what's happened since then, the consumption has increased by about 50%. And for the first time since then, we had one of these companies come forth and said we could not actually procure enough carbon-free energy to meet our net zero goals. So, and even say, that's in the short term, like this is not a problem that we are close to solving. And even if we solve the accounting problem with carbon credits, there is a question of the energy needs to be available at the data centers where and when they need them. And the, AI training we've seen AI training has actually increased in our data centers compared to where it was, with respect to compared to inference and research. So there is an opportunity here to actually shift the load to when and where renewable energy is available, and we could and should be working on some of these technologies. This is getting more complicated by regulations because we cannot actually run AI anywhere we want or where renewable energy is available. There are geographical regulations around where this can be done. So this is going to add a layer of complexity to whatever we do as computer scientists. So, so in the short term, there is problems that we could be working on. I think in the long term, when we solve this operational energy problem through renewable energy, we still have the question of what happens to the manufacturing process. So, we have, if you look at the life cycle, you manufacture it, you transport it, you use it, and then you decommission it. So we have solved one of those 4 problems here. The other 3 still, like I said, 70% of our emissions at Meta came from those other 3 steps in the life cycle. So that's the problem we still need to address.
Yeah, just piggybacking off of Rami's answer there. So in the manufacturing phase, right, you could try to apply the same logic to say, oh, why can't we have green manufacturing? Like get Intel and TSMC and Hynix and Samsung their own nuclear power plants or solar farms? And does that solve the problem? Well, not necessarily, because almost half, but really around like 40% of the carbon emissions from manufacturing are coming from chemicals, gases, and materials that are being used to manufacture the chips, right? And so even if we were to solve the operational problem or the green grid problem, right, that process still remains. And so I'd venture to say, like, in the short term, no, we can't rely on greening the power grid to kind of circumvent this. And in the long term, I don't know if that's a sustainable solution. But even if it is, you're still leaving this manufacturing piece on the table.
Great. So let's open it up to audience questions.
Thanks. Hi, Ariel here. So I'm kind of struck because when the question of the R's of circularity, which you've mentioned 3 of the 9 of them, and you were talking a lot about, right, this idea of how do you redistribute, how do you design for modularity, things like that. That all touches, of course, on the main system of circularity, which is embedded in cascading loops, partnerships, et cetera. You're also talking about kind of this disconnect in the manufacturing world of, how emissions are impacting it, but of course it's not just emissions, right? It's biodiversity, water, we could go on and on. So I'm interested because when kind of that question came up, Professor Lee was the only person who actually spoke to these R's of circularity or circularity at all. And then it seems like there's kind of maybe a disconnect, and I don't know, I'd love to learn more about your perspective on how not only the manufacturing process and the design of these products are incorporating that kind of in your research or at Meta.
Yeah. So there is definitely a lot of people who run these data centers looking at circularity. One is looking at how long are we currently using the components that go into these data centers, and has their lifetime changed over the last few years, and actually what can we reuse and how do we actually extend the life of these devices. So definitely there is work going on. I think I didn't speak much to it since it's not necessarily something that research is looking at, but we have our data center operations team and infrastructure heavily investing on circularity for the infrastructure components.
Hi, my name is Ollie. I had a question on quantum computing and how that emerging field factors into this discussion on sustainable computing.
So I view quantum as distinct class of computing, and I also am not betting on it. So in the sense that it's not gonna be a drop-in replacement for anything we imagine AI to be giving us today. So I think there is some sort of small tangential connection between sustainability and quantum, which is to say that some of the technology being used to do cryogenic cooling for qubit design could also help improve energy efficiency. So there has been renewed discussion about cryogenic computing cooling down the servers to incredibly low temperatures so that they run in a more energy efficient way. But that's also, I feel, a much more speculative solution than anything we've sort of talked about.
Hi. So I wanted to know that when the data centers are built, we typically have resistive load banks that are used for testing, UPS or these large power systems, but those systems could be potentially regenerative. Is there work that's typically going on, or research that's considering how to replace that? Because that seems like something that could potentially save a lot of electricity for the data centers.
So I know of some work where people are looking into sort of how to integrate this type of generation of the data center with the grid, where data center can give back into the grid when they have extra and vice versa. But I think I'm not sure whether they're actually like being used right now or they're still in the research phase. But there's a lot of interest in co-optimizing multiple infrastructure that depend on each other, like the water infrastructure is related to data center, which is related to grid, but the electricity is also used for the water infrastructure, sort of this cross-domain, cross-industry collaboration across different types of resources. There is a lot of interest that people are looking into. This type of research is typically difficult because it's even more interdisciplinary and people from very different backgrounds have to collaborate, and that's why I think they are slower moving, and many different sort of entities are involved, and convincing everybody on sort of a common protocol and shared values is also quite difficult to make them practical.
Hi. If there was one piece of advice that you could give to someone developing AI systems and machine learning models, what would that be? And where could we stay informed of the latest advancements in sustainable cloud computing?
I guess if someone is interested in developing some new AI capability, you've heard maybe mention of the computing stack a couple of times, and one of the key principles behind computing is the notion of abstraction, which is to say you don't need to reason about transistors in order to write your program, right? So there are these multiple levels that hide complexity. So if you are an AI developer, you go and develop your capability, develop your fancy model, show some amazing capability, and hope that the system architects are working a few layers below in the abstractions to give you an efficient system to deliver that capability. So hopefully, to the extent to which software developers need to know about sustainability or carbon or power will be defined through very cleanly defined interfaces. And you only need to reason about one or two metrics coming up from that.
So can I add also? So a lot of us here are more on the software system, computer architecture side, but we're actually kind of cleaning up the mess that the ML people created, right? So so in all seriousness, though, right? These models, if you look at them, they're actually extremely inefficient, right? If you look, like my 4-year-old daughter learned how to speak and understand with way fewer examples than the amount of data, which is basically all the data on the internet that was fed to train a large language model, right? So part of the, I think, challenge is on the ML side is how can we train models with similar or even greater capabilities on a much smaller amount of data with smaller parameters, right? I think that's the kind of grand challenge for AI, which would also help a lot for sustainability.
Sure. Maybe to jump in on that for a second. I mean, I almost push back a little bit on where like the systems and computer architects are trying to like clean up the mess of AI. I mean, there's this whole notion of like hardware lottery, right? Of the hardware that becomes successful needs a killer application, and the killer applications need the hardware backend as well. As computer architects and system engineers, like we've gotten really, really good at matrix multiplication. And there's a reason that these models look very much like that. So I think there's a lot of opportunity in terms of developing new AI capabilities, right? Like reimagine, well, what if you could maybe not completely give up on kind of like the boundaries of conventional like GPUs or something, but what if you had other capabilities, right? An example of this would be sparsity. I think rewind the clock maybe 8 years. No modern high-performance GPUs or AI accelerators had sparsity capabilities because, like even in industry, the conventional wisdom was scaling out regular computation is just way more efficient than trying to exploit irregularity in a single node. Now we're starting to see some of the latest GPUs start to support this capability. And so one thing that I would think about is like that co-design opportunity of if you had slightly different hardware capabilities, if you had slightly different system capabilities, what could you do?
Time for a few more questions.
Somewhat related to the last question, you mentioned, Professor Lee, that there's a lot of optimization already in like data centers hosted by Google and Amazon, and there's also a lot of software that these companies host for other companies as well as architecture. And so I'm thinking, is there any sort of optimizations that are happening at the software level? For example, like the optimizers of SUSE that could be leveraged by companies that are using the platforms provided by these already like hyper optimized companies.
She mentioned Zeus.
Yeah, I can. I can take a crack. So, like, what we've been trying to do is focus mostly on the software side of things, because typically energy efficiency, power efficiency, carbon, they have been unexplored for a long, long time in the hardware community, because there's a lot of inefficiencies, and they've gotten better and created very good hardware. But what is often true is that 2x gain in hardware is like lost many more times in software, because at the software level we have too many abstractions that are just layers and layers of bloating basically gets added up. And I think by being able to measure exactly how much energy is being consumed or carbon is being sort of emitted throughout the sort of software side of things, we can sort of save a lot of those without having to make any changes to models or hardware. And that is sort of like free you can get without even having to deal with like accuracy loss or other things. I think in general, we should be very careful in using anything without measuring. We should always try to measure however sort of much we can, and whatever tools we have available. They may not be perfect, but they are better than just going blind and hoping that it works out. I'll just stop there.
I want to add to that a little bit. One thing, when you showed one of the charts how the numbers you see shouldn't be trusted, because in reality the hardware might not be being used as much as you think it is. We actually published these numbers a couple of years ago in the Sustainable AI paper. So I can't forget exactly how much, but the GPU utilization numbers was well below 50%. The exact numbers are in the paper. So when you go look at what's happening is this inefficiency in software where programs are waiting because the interconnect between the GPU and CPU is not fast enough, or they're bound by memory. So learning about those and maybe designing hardware to work with the demands of the software is something that will significantly improve and make sure that we utilize these machines, because utilization affects both your operational and manufacturing emissions that are coming out.
Last question.
Oh, great. Well, thanks everyone for your time today on the panel. My name's Lauren, and this is maybe outside of the scope of your guys' work on like the software efficiency, but the conversation about like the solar or renewable energy credits and the offsets made me think of this side of it. Is there any discussion about like utilizing the heat that is actually generated at the data centers, like selling it or investing in thermal energy networks as an alternative to, you know, just relying on RECs to offset and become net zero?
I think that there are isolated cases, I think, where thermal energy is extracted from the data centers and used to power homes and generate and provide heating to the local community. I don't know to what extent that has been scaled out. So to my understanding, Microsoft, for example, or Google has demonstrated test cases in Scandinavia, and certainly that's a setting where it makes sense. So I think maybe I'd say all of the above is necessary, right? So if that's a viable solution in that particular context, it makes a lot of sense.
Let's have a warm round of applause to our guests and speakers and Tamar. For those who are joining the reception, we'll meet right outside the hall. Thank you, everyone.